One swipe. A 20 megabyte video starts playing in under a second anywhere on Earth. Under that swipe, upload, transcode, storage, ranking, caching, and a global edge network.
Here is the distributed system end to end. We build it once, then reuse this exact map for every flow that follows.
Clients talk to one API gateway, authentication, TLS, rate limiting, request routing. Behind it, a load balancer fans traffic across stateless service replicas. 4 services split by requirement: upload, feed, social, search. Each owns its own storage. The data tier is polyglot, object storage for bytes, Kafka for events, Redis for hot reads, Cassandra for the write-heavy tables, and a relational store for accounts. Transcoding runs off the queue, and finished renditions are served from the CDN, not from the services. 2 rules hold the whole thing up. The compute tier is stateless and autoscaled, and every piece of state is replicated across availability zones. Zoom in on the front door. Every request from every client lands on the API gateway first. It terminates TLS, validates the access token, and attaches the caller's identity to the request. It rate limits per user and per IP with a token bucket. Abuse gets a 429 before it ever reaches a service. It routes by path and version so services can be deployed and renamed without breaking old app builds. It is also where request tracing starts. One request ID follows the call through every downstream hop. The gateway is stateless. That is the only reason you can run 40 of them behind one Anycast address. Behind the load balancer sits the service layer, 5 small services each owning one requirement. The user service owns accounts, profiles, and the follow graph. Small rows, heavy reads, relational.
The video service owns video metadata and the publish state machine. Uploaded, processing, ready, blocked.
The feed service only assembles and serves ranked lists. The interaction service absorbs likes, comments, and shares. The notification service fans events out to push, and it is the only one allowed to talk to the mobile push providers. One rule keeps this honest. A service never reads another service's tables. It calls its API or reads its events. Follow one upload. The client asks the upload service for a pre-signed URL and sends the file in chunks. Chunking means a dropped connection resumes instead of restarting, and bytes go straight to object storage, never through the service. The service writes one metadata row, marks the video processing, and publishes an event to Kafka. A pool of stateless workers consumes that event and transcodes the master into an adaptive ladder cut into short segments. When the ladder lands in storage, the row flips to ready, and the video is publishable. The user never waited. Where do the bytes actually live? In object storage, flat, cheap, addressed by key, one upload becomes a folder. The master file, one folder per rendition, and a manifest listing the segments. Each object is written to 3 availability zones. Durability comes from replication, not from backups. Okay. Lifecycle rules move cold videos to cheaper tiers after 30 days. Most views happen in the first 48 hours. The CDN sits in front, Edge POP, then a regional cache, then origin. Only a miss at all 3 touches storage. Hit ratio is the number that pays the bill. Above 90%, origin egress becomes a rounding error. Now the read path, the one that has to be fast. The client asks the feed service for a page of videos. It gets back metadata plus a manifest URL pointing at the CDN, not at our servers. The nearest edge POP already holds the segments. A cache hit answers in tens of milliseconds. A miss pulls once from origin, fills the edge, and every later viewer in that region hits cache. The player prefetches the next clip while you are still watching this one. That is why the feed feels instant. The interesting part of the feed service is not serving it, it is choosing what goes in it. Candidate generation pulls a few thousand videos from cheap sources, follows similar creators, trending in your region, fresh uploads. A feature store joins them with watch history and video signals, and a ranking model scores every candidate. The top few hundred are written to Redis as a pre-computed feed, so the request path is one cache read. Watch time, completion, and skips flow back through Kafka into the next training round. The loop closes. The queue is the spine of everything asynchronous. Producers append, consumers read at their own pace. A topic is split into partitions, and the partition key decides ordering. Okay, video ID here, so one video's events stay in order. Each consumer group keeps its own offset, so transcoding, notifications, and analytics all read the same events independently. Delivery is at least once, so consumers must be idempotent. The same event twice must not double count alike. Failures retry with backoff into a retry topic and give up into a dead letter queue that a human can inspect. And because the log is durable, a slow consumer is a lag graph, not lost data. Now, the data itself, 5 entities carry the whole product. A user has an ID, a handle, a profile, and 2 denormalized counters, followers, and following. A video belongs to exactly one user and carries its caption, its storage keys, duration, visibility, and a view counter. A like and a comment each point at one user and one video, the classic many-to-many made explicit as its own table. Follow is the same shape pointing at users twice, follower and followee with the pair as the primary key. At this scale, you never join these tables, you store each read shape separately and keep them in step with events. In code, those tables become a small domain model. Objects with behavior, not just rows. A user can follow and unfollow. A video knows how to publish itself and how to expose its playable renditions. Media is composed inside a video, no media. That is composition, and it is why deleting a video deletes its objects. Interactions and comments are separate aggregates that only reference a video by ID, loose coupling on purpose. Feed is not stored as an entity at all. It is a projection, a list of video IDs rebuilt from signals. Keep the boundaries here and the services above practically draw themselves. One machine cannot hold the likes table, so the data is partitioned, and partitioning needs a rule. Hash the partition key into a token ring. The node that owns that token range owns the row. Write it to 3 nodes in 3 zones. A write is acknowledged when 2 of them confirm. Reads also ask 2. 2 plus 2 is greater than 3, so a read always sees the newest write. Add a node and only the neighboring ranges move. That is the whole point of consistent hashing. A viral video takes 1,000,000 likes a minute. Writing each one to a row is how you melt a database. So likes become events. Kafka absorbs the burst, a stream job aggregates in short windows, and only the delta is written. The number you see comes from Redis, updated optimistically on the client, corrected within seconds. And when one key gets too hot, split it. Shard the counter across buckets and some on red. 2 features hang off the same event log, search and notifications. A search is a separate index, not a query on the main store. Events stream in, get tokenized, and land in an inverted index. That gives prefix suggestions for creators, hashtags, and sounds in a few milliseconds without touching the write path. Notifications fan out on write for normal accounts and on read for accounts with millions of followers. Otherwise, one post becomes 10 million writes. Both are asynchronous, so if either falls behind, uploading and watching keep working. Step back and look at the same system as layers instead of boxes. This is the scalability view. Traffic hits one Anycast address, spreads across load balancers, and lands on whichever service replica is healthy. The service layer is horizontal. Every service is many identical replicas, so capacity is just a number you raise. Underneath, the data and infrastructure layer scales differently. Caches shard, queues partition, databases replicate. Around all of it, metrics and traces, auto-scaling on real signals, multi-zone availability, and security at every hop. Scaling is never one trick. It is picking the right axis for each layer. Last question. What happens when part of this breaks? Because at this size, something always is. The service instance dies, health checks pull it from the pool, and the load balancers stop sending it traffic. No user notices. A dependency slows down, timeouts, retries with jittered backoff, and a circuit breaker that fails soft to a cached feed. A whole zone goes dark, replicas in the other zones already have the data, and the queue means nothing in flight is lost. One map, 5 ideas. Keep bytes out of databases, pre-compute reads, absorb writes with a log, cache at the edge, and let every tier fail independently. Everything else, sharding, quorums, fan-out, auto-scaling, is one of those 5 ideas applied to a specific table or tier. Get those right, and the short video platform is not magic. It is arithmetic plus a lot of caching. That is the whole system, front door to storage, and every part in between. If this helped, subscribe to Codarc Dev for more system design deep dives, or follow Codarc Dev. New architecture breakdowns every week.